Hi all, welcome to the lecture series on Aerospace Propulsion. Myself, Manideep Gupta, Assistant Professor, Department of Aeronautical Engineering from MLR Institute of Technology. Today, the topic which we are going to discuss is about the propulsive efficiency of a rocket and performance parameters of a rocket. So, coming to the overview of today's presentation, we are going to discuss about the propulsive efficiency, performance parameters of a rocket, and also we are going to discuss the staging and clustering of a rocket. So, coming to the propulsive efficiency. What is propulsive efficiency? Suppose if you take a rocket, okay, if you take a rocket, the gases expands, okay, the gases expands through the nozzle. It will generate some velocity Vj. Because of this velocity, the vehicle will get some velocity V. Okay, so how effectively the kinetic energy is converting into the thrust? That is nothing but the propulsive efficiency. The efficiency of the conversion of the kinetic energy of the ejected mass into the useful work to move the rocket is referred as a propulsive efficiency. So, how effectively the kinetic energy of the gases is converted to move the vehicle forward, to move the rocket forward, is explained by the term called propulsive efficiency. So, how do you calculate this propulsive efficiency? The symbol for propulsive efficiency is NP. Eta P is the symbol for propulsive efficiency. Coming to the formula or basic definition, it is NP equal to useful work divided by the supplied energy. So, the supplied energy is nothing but the kinetic energy of the gases or the energy you are providing to the rocket with the help of propellants, and the useful work is nothing but the work done on the rocket. That means the rocket movement, whatever the energy utilized to move the rocket forward, that is nothing but the useful work. So now we have to write the equations for useful work, that is the work done by the rocket, and also the supplied energy, the energy provided to the rocket, the kinetic energy provided. Then we will get the equation for the propulsive efficiency. So if you want to generate an equation for the useful work is equal to force into distance, right? Force into distance. So the force generated, that means the force acting on the vehicle is m dot Vg, that is momentum, rate of change of momentum of the gases, m dot Vg, and the distance per unit time, that is velocity. So here what we are calculating is useful work per unit time. So useful work per unit time is m dot Vj into V. Now it will give the useful work done by the rocket. Here capital V is the velocity of the rocket. Here capital V is the velocity of vehicle or rocket, and Vj is the efflux velocity. Vj is the efflux velocity, and m dot is the mass flow rate, propellant mass flow rate. Right, this is the useful work done by the rocket. Well, now next we have to calculate the supplied energy. So the supplied energy is the sum of work transferred to the vehicle and the kinetic energy of the ejected masses. Coming to the kinetic energy of the ejected masses, how do you calculate the kinetic energy? So kinetic energy is equal to half mv square. This is the basic formula for the kinetic energy. So here what we are doing is we are calculating the F. So kinetic energy per unit time. Okay. Here also useful work done per unit time. Here also kinetic energy per unit time. So half m dot v square. It will be half m dot v square. So half m dot, this is V, right? V. So of the ejected mass, we are calculating for the ejected mass. So whatever the rocket, suppose if you take rocket like this, it is moving with for velocity V, and whatever the gases are leaving velocity Vj. So suppose consider these are the gases leaving with Vj. So if you see the velocity of the actual velocity of these ejected masses with respect to the stationary person, then this velocity will be forward. This whatever the ejected gases will also have some forward velocity capital V, and in opposite direction it is Vj. So the resultant velocity is V minus Vj. This is the velocity of these gases which are left the rocket with respect to a stationary person on the ground. So we have to calculate the V here. So if you substitute V here, then half m dot V minus Vj square is the kinetic energy of the ejected mass. So finally the propulsive efficiency is useful work by supplied energy. So useful work on the numerator. So supplied energy is the sum of work transferred to the vehicle and the kinetic energy of the ejected mass. So whatever the energy transferred, sum of the whatever the propellant burned, it will have some kinetic energy. So but total kinetic energy is not transferring to the vehicle. Only sum of the kinetic energy is transferred to the vehicle. So that is work transferred to the vehicle plus the energy remained left after leaving the while the gases are leaving the rocket. So that means whatever the energy of the gases leaving the rocket, that means that energy is not transferred to the rocket. So we have to add that. So that kinetic energy of the ejected mass. So finally the equation is this is the work done, useful work done by the rocket per unit time, and this is the work transferred to the rocket per unit time, and this is the kinetic energy of the ejected mass per unit time. So finally the propulsive efficiency is equal to useful work done by the energy provided to the rocket. So this is the equation for propulsive efficiency. M dot capital V into Vj divided by M dot V into Vj plus half M dot V minus Vj square. So further we can rewrite this equation. Okay, you can cancel this m dot here, m dot, and if you simplify this equation, then it will become 2 into capital V Vj by V square plus Vj square, and further we can simplify this equation by V ratios, vehicle velocity to the ejected efflux velocity Vj. So V by Vj, you can take a Vj common. Okay, Vj common here, then it will be Vj square, right? 2 into V by Vj divided by 1 plus V by Vj square. And so it is a propulsive efficiency in the ratio of vehicle velocity to the ejected efflux velocity. Okay, 2 V by Vj by 1 plus V by Vj square. So if you observe the variation of this propulsive efficiency with respect to the V by Vj ratios, here you can observe the ratios. So here at the starting, that means where V by Vj is equal to 0 and V by Vj value is less than 1 up to this portion, the V by Vj value is less than 1. Okay, less than 1. So you can increase, you can see as the V by Vj reaches to 1, the propulsive efficiency is increasing, and once the V by Vj is crossed 1, okay, you can observe the decrease in the propulsive efficiency is decreasing. Okay, actually if you observe this ratio V by Vj, V is the vehicle velocity, and this is the efflux, right? Efflux velocity. Okay, so always vehicle velocity is less, always V is less when compared to the Vj, right? So if you observe, if V is less than Vj, what about this ratio V by Vj? If V is less than Vj, then V by Vj is also less than 1. Suppose if V is equal to Vj, here the condition is V is less than Vj condition. Next, if V is equal to Vj, okay, if V is equal to Vj, then what happens to this V by Vj ratios? It will be V by Vj equal to 1 when V is equal to Vj. Next condition, when V is greater than Vj, is it possible? When V is greater than Vj, that means V by Vj will be greater than 1. But this is practically not possible. This V by Vj greater than 1 is when V by Vj is greater than 1 means propulsive efficiency decreases. So this is about propulsive efficiency. Next we will discuss the performance parameters of a rocket. The basic performance parameters is impulse. What is impulse? The momentum associated with the efflux of the propellants from the rocket was seen to provide velocity to the rocket, and the change of momentum is nothing but the impulse. Whatever the gases, exhaust gases, the change in momentum of the exhaust gas is nothing but the impulse for a rocket. So if you go to the impulse, so that is MP into Vj. The units of the impulse are Newton second. Next, specific impulse. So the specific impulse is a impulse delivered per unit mass of the propellant. Impulse delivered per unit mass of the propellant. The specific impulse, the symbol is ISP, and if you write the equation impulse per unit mass of the propellant MP, then Newton second per kg, then you can get the equation, the units as meters per second. So meters per second means we can write specific impulse that as Vj. It is equal to Vj efflux velocity. Next, even we can write the specific impulse like F by m dot MP, that means the force per unit mass flow rate of the propellant, F by m dot P. Then also you will get the same, that is impulse per unit mass of the propellant. Either you can say impulse per unit mass of the propellant or force per unit mass flow rate of the propellant, m dot P. Both are same. The next one is thrust. So the thrust developed by rocket is nothing but the rate of change of moment. Rate of change of moment. So or change in impulse or rate of change in impulse. So d by dt of I, d by dt of I can be written as mpj, and here if Vj is constant, then it will be dmp by dt, and this dmp by dt can be written as m dot p into Vj. So finally F is equal to m dot p propellant m dot p into Vj. The units are newtons. Next, impulse to mass ratio. It is the ratio of total impulse I to the initial mass of the rocket. So impulse to mass ratio I is equal to I by mi. Impulse to the initial mass of the rocket. Next one is total to mass ratio, thrust to mass ratio. Okay, thrust to mass ratio. So it is nothing but the ratio of the thrust produced by the rocket to the initial mass of the rocket. Thrust to initial mass of the rocket. These are all the performance parameters of a rocket. Next, staging and clustering of rocket. So if you go for a multi-stage rocket, okay, if you go for a multi-stage rocket, like this, if you go for first like n number of stages, 3 and so on, n number of stages. Okay, each stage has a mass ratio that is 1 by r. Okay, the first stage mass ratio is 1 by r1. So the delta V produced by this is Vj log 1 by r1. The same way, delta V produced due to the second stage is Vj log 1 by r2. So if I want to calculate the total velocity gained by the rocket, then I have to add the delta V1, delta V1, delta V2, delta V3 and so on, like that delta Vn, n number of stages. So if I write the equation like that, then the equation will be delta V equal to Vj log 1 by Rm1, Vj2 log 1 by Rm2 and so on. Finally Vjn log 1 by Rmn. Rmn is the mass ratio of the nth stage rocket, nth stage for a rocket. Right. And here if I consider the efflux velocity of each stage, Vj1, Vj2 and so on, Vjn, all are equal to Evj. Then what happens? This equation will be simplified to this. Then delta V is equal to Vj. All will become equal. All are equal. So we can common this Vj1, Vj2 and all those. Then it will be Vj log 1 by Rm1 into 1 by Rm2 into 1 by Rmn as on 1 by Rmn for the nth stage of the rocket. And next, further, if I write this mass ratio of the rocket, so this 1 by Rm can be written as what? Mi by Mf of the first stage. 1 by Rm2 can be written as Mi by Mf of the second stage, like that, and so on, Mi by Mf of the nth stage. So this equation can be written like this. And if you observe the multi-stage rocket, the final mass of the previous stage equal to the initial mass of the initial mass of the next stage. Okay, so this Mf1, the final mass of the first stage equal to the initial mass of the second stage. That means Mf1 is equal to Mi of the second stage. The same way, the final mass of the second stage, Mf2 is equal to initial mass of the third stage, Mi of the third stage, and so on, like that. If I consider Mf1 is equal to Mi2, Mf2 equal to Mi3, and so on, like that, Mfn minus 1 is equal to Min. Then what I finally get is Mi1, initial mass of the first stage rocket, divided by the final mass of the last stage. So Mi1 by Mfn. So this equation will turn to delta V equal to Vj log Mi1 by Mfn. Well, initial mass of the first stage and final mass of the last stage or nth stage. This equation is applicable. You can place n is equal to 1, 2, 3, 4, 5, as on, whatever. So you can substitute any number here, then you will get the delta V, the total velocity gained by the multi-stage rocket. Another condition, we are substituting another condition. If the mass ratio of the all stages are same, that means 1 by Rm1 equal to 1 by Rm2 equal to 1 by Rm3 and so on, 1 by Rmn. Then what happens? If the mass ratios are same, Rm1 equal to Rm2, Rm3 and so on, then we can write this equation, the previous equation, as Vj log 1 by Rm whole to the power of n. And if I take this n out of the log, then it will be n Vj log 1 by Rm. That is the mass ratio of the rocket. Condition is mass ratios are constant. Mass ratios of all stages are same. So this is about the multi-staging and clustering. Okay, clustering. Coming to the clustering, we generally use clustering at the time of initial first stage to overcome the heavy gravitational force acting on the rocket, like a solid rocket boosters, for clustering. Okay, so this is about the equation of a multi-stage rocket and clustering. So coming to the summary of today's rocket, we have gone through the propulsive efficiency and the variation of propulsive efficiency with respect to V by Vj, and we have gone through the performance parameters of a rocket, that is impulse, specific impulse, impulse to mass ratio, impulse to thrust to impulse, and parameters, and we have gone through the staging and clustering of the rockets. Thank you.